And finally, you write your kernel, which is k of xi xj, as ui transpose uj, and u is this. You know that Nystrom approach is of order of nmd plus m3. So let's talk about sketching. I've talked about that idea of random matrix, and all of them now make sense because it's just we are just doing it for least square regression, but in general you can use this new paradigm of sketching for almost any problem. But you know, there are very few articles that are not related to least square regression. So sketching for least square regression. So I said that the problem is we want to solve this. Ax is equal to b, and you know the answer is just A transpose B. But it is of order of nd squared, and it is hard to do the inverse in practice. And that's why people go to some other faster ideas, such as sketching. You want to sketch matrix, and so we draw S from k by n random family of matrices, but k should be less than, very, very less than n. And then you compute SA and SB. This is k by 1, this is k by d. And finally, you minimize a much simpler objective, which is SA x minus SB 2. An interesting intuition is you can consider that this is your objective function. For example, this is your objective function. With any sketch, because you are concentrating on some small subset of your samples, that's why you get something like this. So your minimum is just suboptimal. With another sketch, you get this. You know, you get this. With another sketch, you may get this. But what is a good sketch? A good sketch could be something that can cover something like this, and almost the optimal solution. And it is almost optimal solution. So the distance is small, this distance is small, so this is the best sketch you can get. So that was the intuition behind that. But how should we choose the right sketching matrix S? S could be d epsilon 2 by n matrix if you use IID normal random variable. This is the naive approach. And also you can use subspace embedding ideas. And we say that Sk by n use it from IID normal random variable that for any fixed d-dimensional space, the column space of n by d matrix A should satisfy SAX2 is equal to 1 plus minus AX2. It means you preserve the norm. If you multiply this S matrix, still the norm of them are similar. Of course, there is an epsilon error, but it is quite similar. So entire column space of A is preserved. And now consider the subspace L spanned by the columns of A together with B. So of course we have a D plus 1 dimension, and Sy is equal to 1 plus minus epsilon y, and hence we can write Sax minus B 1 plus minus epsilon Ax minus B, and we solve this problem, which is much easier. And you solve it in poly d over epsilon time, which is so fast. But hey, wait, you are calculating this SA, okay? It takes time to capture, since both S and A are, this is dense, so it takes ND squared. So the order of complexity, the time order, is order of ND squared time. So what are you doing? You're not improving, because both of them are dense. It takes time. So that's why people use some other methods, such as some practical, let's say, methods that, for example, S is a sampled, randomized Hadamard transform. So S is PhD, but D is a random diagonal. You get +1 with 50% chance, you get -1 with 50%, and H stands for Hadamard. You know, Hadamard is like this. And your P matrix, it is just a random small subset of rows of H and D, HD. So it's a random small subset of HD. Now SA can be of order of ND log, which is a quite improvement. Of course, there are many other methods, such as count sketch. And let's just talk about low-rank subspace clustering. So low-rank subspace clustering is one of the first methods for subspace clustering. K-means, the traditional way of clustering is that you get a ball, you put all of them inside, and so your distance is like a square, it's like a sphere. And but you can define your cluster in a different way. For example, say, instead of just a ball around one point, you can say that this could be your subspace. Your points are inside a plane. A plane, for example, alpha x plus beta 1 is equal to gamma. In any dimension, of course. And even I've seen some people use cones. So not only ball, not only plane, but also they use cones. So that they say, if the points lies on this cone, then you can cluster those points. So this is another cone. So this is cluster A. This is cluster B, because points are on that cone. So cone, plane, and ball, there are different ways to find your cluster. So low-rank subspace clustering is just using planes. So this is one of your clusters. This can be another cluster. For example, these two planes are orthogonal or most of the time have angle theta. But if this angle is too small, for example, if the two planes are very, very close to each other, then this method will not work, because sometimes you cannot distinguish signal and noise, and that is the limitation of some algorithm. So we want to find these clusters. So this is cluster A, this is cluster B. And of course, your planes does not have to cross the origin. For example, this is the third cluster A, B, and C. They intersect at this point. This is the origin. This is the main assumption that many people use. But in reality, when you are trying to approximate your manifold, people in manifold regularization problem, they approximate it like this. The reality is that they can have some intersections, but the intersection is not the origin. So you approximate your manifold by some patches, but each patch is a linear subspace. But this is more general. Still, it is not. You have. It's like you have tried to approximate a very nonlinear function by some linear functions like this. And you call it. This is cluster A, cluster B, cluster C, cluster D, and this is cluster A, cluster B, cluster C, cluster D, cluster E. You're approximating it. So we have a very, very nonlinear manifold. You approximate it by some planes. This is one paradigm. The other paradigm is that, okay, we approximate some points with some cones. This is very new. Many few people are working on this. So this is a cone. So you are approximating your manifold with some cones. Here you have 4 cones. You have 4 clusters. But in reality, you should know the structure of your manifold, which is a difficult problem. And based on that, you can see what kind of norm you need. We have 0 norm, L1 norm, L2 norm, L infinity, and a combination of different norms allows you to understand, to cover all of your nonlinear manifold. Okay, so you enjoyed the intuition behind this. And subspace, unlike locally LLE, which was local linear embedding and approximated with some patch locally, but and it was it was a ball around that, because k nearest neighbors, you wanted to minimize that. But unlike LLE, now we are approximate your clusters by planes. So you write each point as a linear combination of different points. You may say that, okay, we can write it in different ways, infinite ways to write one point in terms of the other. But by using sparsity, you will see no. There are just a few points that are essential, and the other points are just linear combination of those few points. So we want to minimize j from 1 from n and sigma xj minus xi cij squared, the L2 norm, and in local linear embedding, you are doing this by saying that we have. It's very similar to that. Sometimes you forget that this is not LLE. So instead of LLE, you want to write x as a linear combination of other points. And this is the weights that you want to find. So C is unknown. You want to know which combination should we use. So the simplest solution is that, let's say C is I, but it is useless. It's a bad solution. And that's why you figure out that CII should be equal to 0, because you don't want to write a point in terms of itself. Okay, it doesn't give some information. So we penalize C so that C is equal to I is not a solution. So Ni is the number of points in subspace I. Di is dimension of subspace I. Xi is data points, and rank of Xi is Di. These are the common notations. And so if X is inside the I's subspace, then there exists C such that X is equal to xk ckj for k's that xk is inside Si. Because Sj has rank dj, then X should only be linear combination of dj points. Suppose rank of X is equal to R, which is less than minimum of D and N, then rank of X is rank of XC, because we want to write each point as a linear combination of, and this one is less than minimum of the two parts which we have multiplied. So this is the minimum of rank X and rank C. Because rank of X is R, which is and R is less than rank of C, so this is less than R. So the problem is that we want to minimize rank of C subject to X is equal to XC. So as you know, matrix is SVD. Everything about a matrix can be revealed by its SVD. So that's why it's so traditional. And X is U1 sigma 1 V1 transpose. This is the compact SVD form. So now this is D by R, R by R, and R by N. So just take C is equal to V1 transpose, and you get the minimum rank. And of course, you will notice that in practice, everything is noisy and you cannot do something like this. So it is useless. But it has a good intuition, geometric intuition. U sigma V1 transpose V1 transpose, because this one is I, so this one is X. I want to prove that the theorem is that